Hi, this is George Fairbanks, and today I'm going to talk hopefully quickly about what software architecture is all about if you see it as a set of abstractions. And the reason I'm chatting about this is because there was an interesting thread on Google+. It was in regards to an article that I just recently wrote about why it's getting harder to apply software architecture. And a coworker wrote to me and asked a really great question, which is, he says, I understand software architecture is a set of design decisions that are hardest to change. So what does it mean to say you're applying software architecture? Is that meaning you're applying your decision-making skills or what? And there was a bunch of other good context in this, but I'm just going to focus on that one question of what does it mean to be applying software architecture? Now, when I look at the entire field of people that are writing about software architecture, I see three distinct ways that people think of what software architecture is. The first thing is it is the least specific. It says that software architecture is a social construct, okay? If I say that's architectural, then it's architectural. That is, if our team says it's architectural, it's architectural. The second is more specific, and it basically says the team will make a set of design decisions over time, some of which are really hard to change. Let's call the hard to change decisions software architecture. But it doesn't really go beyond that. In other words, there are all kinds of decisions a team makes. And so, for example, some people might be uncomfortable with the idea that choosing a language, programming language, is architectural. Okay, but on the other hand, choosing a client-server architecture clearly is architectural. The third big idea is that architecture is a set of abstractions, just in the same way that like method signatures are abstractions, or abstract data types are abstractions, or state machines are abstractions. And that we haven't been very good about nailing down exactly what those are, but that we have a limited set that we think applies to a lot of different projects. Okay, and so it's that third definition that the article is talking about. So let me dig into that some more and figure out where these other two definitions came from. The first definition, that architecture is a social construct, I trace back to an article that was written by Martin Fowler in the early 2000s. There was a lot of discussion in the early 2000s, by the way, about like what the heck is software architecture, and so this came out of that. So in his article, he quotes Ralph Johnson, and I think Ralph Johnson is a sharp guy, as is Martin Fowler. Ralph Johnson is articulating the idea here that really we should be thinking about software architecture as the set of decisions the set of ideas that the team decides are architectural. And he makes the case that on each project it's a little bit different, and if the team members don't think it's architectural, nobody can contradict them. Okay, so that's that first idea. A few years ago, actually many years ago now, I did a short video essay, which you can find at this link, and it's basically arguing against this. And instead it says that instead of the set of ideas being completely arbitrary, like, my team decides that the color of the web page is architectural. Instead, it should be traced back to a set of failures. That if the team says this could cause the program to fail or not behave as we expect, well, then you can call it architectural. But if you can't trace it back to a failure risk, well, we can exclude a whole bunch of those. Okay, so you may or may not agree with this reasoning, but you can check out that video if you want to learn a little bit more. So the second idea about what is software architecture also traces back to this article. At least it's very well expressed in this article. So Ralph Johnson, again, being quoted by Martin Fowler, gives a second definition. And he says architecture is the decisions that you wish you could get right early in a project. And so Fowler then riffs on this a little bit, and he ends up with, so you might end up defining architecture as the things people perceive as hard to change. Pretty interesting, eh? Because this is much more specific than whatever the team decides is architectural. And in fact, we do perceive ourselves as projects go on as making decisions. So there is also another thread that I haven't picked up here, which came out of the academic world. And sometime in the early 2000s also, the academics started looking into design decisions as as a proper abstraction. And in fact, the industry got in on the game too, and there's this idea of architecture decision records that get written down with a project. These are absolutely great, and they're way easier to think about because you, on a team, you know when you are confronted by a choice, or usually you do. You're like, we've got to make this choice. Are we going to do this or are we going to do that? And often that's at the same time you're writing some code. Okay, so you're in there making a decision. So the idea is let's write those decisions down so that the whole team can see them. And that's great, because that means that if you come to a team new, you can take a look at all the decisions and you can sort of recreate in your head the reasoning that got you to where you are. So the third idea, and the one that I'm going to spend most of the time on here, is that architecture is a set of abstractions. And I'm going to trace this back to the work of David Garland and Mary Shaw and some other collaborators over at the Software Engineering Institute. They work at Carnegie Mellon, and the SEI folks are also affiliated with Carnegie Mellon. I'm thinking of like Paul Clements and Len Bass and some other folks over there, Rick Kaseman. So Mary and David wrote this paper in 1994 as they were trying to sort out what is software architecture, because it, as Mary tells me the story, she was chatting with a bunch of folks, and as she looked at different architecture diagrams, so-called architecture diagrams, there wasn't much formality to them, she was noticing some commonality between these things, and a lot of common terms were being used. And so she's trying to sort that stuff out and see if she could bring a little bit of rigor to it, which would allow us to think about things. I still think that this paper from 1994 is still it holds up as a fantastic introduction of stating what the problem is. And really that's what this paper is. It's not saying this is the answer. It's early days. They're saying we're looking for a set of abstractions that would allow us to reason through this kind of problem. Okay, and in full disclosure, David Garland was my thesis advisor. Okay, so I'm not a completely impartial person on this stuff. I partly chose to go and do work with these guys in grad school because I thought they were doing good work. So here's the rationale for looking for abstractions for software architecture. If we are confronted with a real world problem and it's super easy, you just solve it, right? Like this is the way it works in all kinds of engineering. But if you look at other kinds of engineering, you find that when the problem is complicated, what you do is you look at the real world embodied problem, you abstract it up so that you can reason about it in some space that's more tractable, that's easier to think through. So for example, if you say, I'm going to build, we always talk about houses. If I'm going to build a house, oh my goodness, a house has a lot of details into it. Well, you extract it up and you think about one dimension of it, say like the electrical system or the framing of the lumber, and you ask a question of that model. You say like, will this framing support the house, or is it going to blow down if the wind is very strong? You move that over, that is, you solve the problem. You say this structure, this house should work. You're still dealing with a model, and then you concretize it, okay? That is, you say, here's the model I have of the timber frames of the house or the balloon frame of the house, and then I bring it back down and I build that house, and hopefully it solves the problem. So that's the big idea, is that you have problems that are too hard to solve, you map them into a set of abstractions that let you reason about the problem, and then boom, you end up with a way of solving the problem. So we were used to this style of problem, right? You know, when you had the two traveling trains problem, you start with an embodied problem, you map it into an abstraction, which in this case is algebra with a variable. You're able to reason about it in that form, and then you can come back and say, I can tell you something about the world, that is, when these trains specifically will meet as a result of going through the models. So in software architecture, we're looking for the same kinds of models. And in full disclosure, nobody thinks we've got this nailed, like it's a solved problem or anything like that. You might look at other simpler problems in programming and say, method signatures, we're doing pretty well. We've got sort of that figured out. Subroutines, okay, we've got that figured out. Like there's a bunch of things where like, okay, those are pretty squared away, or state machines and whatnot. But when we talk about software architectures, we do have some abstractions, and they work pretty darn well. So what I've just shown you here is three different diagrams of a system. It's actually, this is a system from Rackspace that I discuss in the first chapter of my book on software architecture, Just Enough Software Architecture, which is free for all Googlers. So go/Just Enough Software Architecture, and you can get the book. So the question here I'm asking though is, compared to reasoning about three different implementations or three possible implementations by looking at models or diagrams like this, how long would that take in comparison if you had to read the full source code for three different implementations? I mean, the obvious answer is reading source code takes a whole long time. Reasoning about abstractions is really easy. I would prefer to do that if it gave me decent results. So let me give you a quick little example problem about making sure you understand what the abstractions are really important. If I gave you this number sequence and you're trying to figure out what the next number is, you might be a bit surprised when I give you that this is what's coming next. On the other hand, once I show you the abstraction, it's going to be completely obvious. It turns out what I was doing is I was grabbing the sequential Wednesdays from this particular calendar in early 2021. And so once you see that abstraction, it's like, ta-da, of course, this is like really easy to figure out. But what we're looking for when we come up with complicated problems in software design is, what are those abstractions? And you have to ask yourself a couple questions. The two questions I think you have to ask yourself are, first, where do the abstractions exist? Okay, that is, are they only in my head, or do they somehow escape my head and make their way out into the world, for example, so that I could see them in a design document, or at least that the entire team shares them, okay? And that's a big distinction, because the alternative is each developer on the project could actually have their own set of abstractions about what the design is or what the architecture is, as opposed to actually you're striving for a world where the entire team shares that set of abstractions about what the design or architecture is. The second question is, if I come up with a set of abstractions and I am using them, do I find that those abstractions are universal or somewhat universal? That is, can I take the abstractions and apply them to this project, which is a device driver, and another project, which is a web server, and another project, which is a web application, or another thing, which is a thermostat, right? Like, how universal are these abstractions? And what I would say is, I think we've gotten to the point where there's a bunch of abstractions which are generally useful. They are I don't find that they're the end. That is, you will always have to add some abstractions on every project. But the flip side of that is, if you don't start with these abstractions, generally the team will be missing out on something, right? They'll sort of kind of forget about some of these. So what I'm going to do in the rest of the talk here is walk through a timeline of what I think the critical abstractions are in software architecture that allowed us to get to the point where we are today. So what I've got here is about this many, something like a dozen. And what I'm going to do is I'm going to group them by categories. And some of the categories I've sort of force fit, but just, it's easier to think about them in groups. So the first group of architecture abstractions deal with interfaces and specifications. So here's the group. The big idea is that we design software, and we do so by indirecting implementations from the interfaces, okay? And so this started out back in the 1940s. Let's take a look at the first one. In 1947, it was clear, even at the time, that we understood the distinction between algorithms, say, that took more memory, or algorithms that ran faster. Okay, so we could get algorithms to run faster if you gave them more memory, but sometimes you didn't have that memory, and so you'd have to choose a slower, more space-efficient abstraction. Okay, and so even at that time, even though you didn't have separable compilation targets, for example, even though the code was monolithic, there was this understanding that you had to distinguish between, I have a sorting routine and I have a fast one that uses a lot of memory, or a slow one that uses not very much memory, all right? So we'd already disentangled the idea of functional requirements, sorting, from quality requirements, which is uses memory or runs faster, okay? And later on, we generalized that much better, which we could say there's quality attribute requirements like, is it usable? Is it reliable? Does it have low latency? So forth. The second abstraction came not much after, and I've had a hard time pinning this one down, but certainly by the 1960s, with Algol, we had an opportunity to separately compile something versus link it, which gave you the opportunity to say, I want to use a sorting routine, but then make the decision later on about, do you want the one that uses a lot of memory or the one that it runs slower? Okay, so you could separate those two. And so that is a second critical abstraction, which is the separation of the interface, which is I want to sort this, from the implementation, which is it going to use a lot of memory or not? Okay, and of course we use that all the time today. We sort of take it for granted, but it was a big deal at the time to make that leap. The third kind of specification or interface abstraction is in the early 1970s. David Parnas figured out some critical ideas about information hiding, okay, or as we call it, encapsulation. And what he said was he saw his coworkers separating the interface from the implementation, but they did it in a sort of naive, straightforward way. And I think we still do this a ton today, believe it or not. So an example of what Parnas was talking about was if he said, if I look at this application and it's got 3 major features, I make 3 major modules and I put interfaces on them, okay? But he said what he's noticed is that doesn't work out really great. It doesn't work out great because with each of those interfaces, they ended up revealing something about their internals, about how they were implemented, okay? And what he said was you could actually take a look at that same problem, and if you decided there was something that you might want to change later, let's say you stored it as a linked list, but you might want to change later to an array or some other sort of implementation choice, then you would build different interfaces. You wouldn't line up the interfaces with like feature 1, 2, 3, because feature 1, 2, 3 probably depend upon the data structure that gets passed across. And at that point, you've just lost your ability to change the data structure. So he said, if I could put this in modern terms, okay, that when you mechanically on an object put getX and setX to hide the variable x and y, you are not actually encapsulating things. On the other hand, if you had a bank account and you said, I would like to debit or credit from the bank account, but you don't reveal directly access the tables or the data structures that you have for your bank account, well, that could be encapsulation, right? That would be better because it would allow you to change your internal representation. Okay, so those are the 3 interface or specification kinds of abstractions that I think are critical for software architecture. Let's switch next to views. Now, if you take a look at views in every other engineering discipline, you're going to find they're used ubiquitously. So for example, if you think about, again, back to houses, you've got a top-down view, you've got a side view, you've got a landscaping view. All of these are different views, and you need the different views so you can reason about different things. So for example, if I gave you a view of the house that showed the landscaping and you said, well, where should I put the air conditioners? Well, that only gives you a little bit of insight into where to put the air conditioners, right? You really want some other view that talks about heat movement through the house. So the first version of this that I can find is the distinction in the late 60s between static views and dynamic views of the code. And you remember when Dijkstra is talking about in GoTo Considered Harmful, he says, you know, when I look at the source code for a program, in order for me to reason about whether it's doing the right thing, I have to make a leap. I have to look at it statically and imagine what it's going to do dynamically at runtime. Okay, and this is the first example that I've seen about not only recognizing that there's 2 different views of the code, which is at compile time and at runtime, which obviously to us is really obvious at this point, but he's making the connection with reasoning, right? He's saying you want to structure your code so that you can enable this reasoning about what happens at runtime. And this is what structured programming was all about, right? Again, something we take for granted, like we use for loops and while loops and structured constructs as opposed to the things that you would be allowed to do in assembly language, which is you could write a goto statement, you can write all kinds of code and all kinds of iteration constructs, for example, that don't adhere to simple ways of thinking about it. And as a result, if you do those things, you're going to have a hard time reasoning about runtime. Okay, there's a great article called "The Story of Mel," which talks about, it's in the sort of programmer lore thing where someone's trying to reverse engineer a program to make a change to it, and it turns out this program is nearly impossible to reason about at runtime. But it's a delightful read. I recommend that one. So that particular insight was that you've got at least 2 views of your code, the static and the dynamic. Now, later on, in fact, much later on, it wasn't really until the 90s that we started talking about other views between the static and dynamic. And the key paper here that most people point to is Philippe Cruschen's 4+1 architecture views, okay? And he says, look, when I design code, and he was a practitioner, he said, well, like when I'm designing systems, I often want to know things beyond just static and dynamic. I want to know, for example, about concurrency, right? Because if I have two different systems and they both are, working independently of each other, they're both running in parallel, well, then I have a different set of problems. And so I need to know about that so that I can reason about it. But really, this was the beginning of an explosion of other different kinds of views that we now use today. And the takeaway message here is there's going to be no single view, and therefore no single diagram that succinctly describes your system, right? You're going to need multiple views. Consider, here's another one that we deal with all the time now. Besides static and dynamic, we also deal with a deployment view. And so your question should be, what code is in production right now? And obviously that depends upon how our DevOps infrastructure has pushed it out and whatnot. And in fact, it might even be more complicated. It might be a certain set of users are in the canary group and they're seeing version 2, whereas the rest of the world is seeing version 1. Okay, so that becomes another view that's tricky to think about. So big architecture abstraction, you're going to need multiple views of the system so that you can reason about different properties of the system. Another one that came in here, and again, kind of obvious in hindsight, is that there are irreconcilable views. So what is a reconcilable view? Let's go back to houses. So if I told you that this is the top-down view of my house and the side view of my house and the landscaping view of my house, you can imagine a CAD program that could like have an internal representation that's a 3D. And if I just asked for any view, top down, from side, landscaping, it just spits that out, okay? Or I could even slice through the house diagonally and it could spit that out. So any three-dimensional view I can reconcile into that, or say any view that can be reconciled back into 3D is just a reconcilable view. And even if I say, like, here's the electrical view of my house, I can imagine that 3D view of the house having the electrical wires, and I could like conceptually like pull away the walls so I just see the wires and where the circuits are. Okay, so even that is reconcilable. But consider other dimensions of your house, which are pretty important. You may have regulations that apply to the house. So for example, how far must the house be from the road? Okay, how close to the property line can you build? Are you allowed to have barn animals? Like, can you have chickens at the house? Well, maybe that is dependent upon the design or how much square footage or how it's zoned. But all those questions are difficult to reconcile with a 3D view of the house, even a very, very detailed 3D view. It's almost like you can't consider how you're going to put the two together. Okay, so the idea here is view types. Okay, so some views can be reconciled, other views cannot. And so the critical one when you think about software design is because of the halting problem, we can't look at source code and always be able to know what it's going to do at runtime. So therefore, those two views are not, strictly speaking, reconcilable. Like oftentimes they are because we write really simple code and therefore I can imagine what happens at runtime. But here's another view, which is the deployment view. Now, in the old days, it was pretty simple. How do I know what code is in production? Well, it's the code that I manually put on the server, okay? But today it gets a little bit more complicated, as we talked about. There could be multiple versions running on different customers. So actually reasoning, if you're like looking at source code and then you ask the question like, what bugs am I seeing if I look at, say, reporting of my system running at runtime and I'm looking at the source code, I really need to understand what version of the source code is deployed in order to reason about that problem. And just looking at the source code doesn't tell me what version of the code is deployed. So that idea of you have view types is a pretty interesting one as far as the software architecture abstractions, because it lets you know the limits of how well you can reconcile views. Okay, next big category is in terms of patterns inside of software architecture. There are three things here that we started naming patterns, then we moved into this idea of the connection between patterns and qualities, and finally the idea we generalize this, okay? So in the early 1990s, like I said, when Mary Shaw was starting to do work on this, she tells me that she rented a conference room, or like secured one, like a reserved one in the building. And for about a week, she just took all these diagrams of systems that she possibly could, and she put them all over the wall, like one of those movies where they've got the crime scene and the person's trying to connect the dots. And she literally was doing that. And she's taking these diagrams and she would clump them together in terms of similarity. And what she found was there were a handful of named things that people were already talking about because engineers have had to design things, and so they came up with terminology for it. So things like client server or layers or pipe and filter. And so what she did was she clumped those diagrams together. Okay, so we started naming those back in the 1990s. What happened quickly afterwards was there was a recognition that the patterns that you use would either make it easy for certain qualities in the software to be there or hard, okay? So for example, here's changes in algorithm, data region, function, performance, and reuse, and whether the architecture patterns of shared memory, abstract data types, events, and data flow promoted those with the plus, or minus means it inhibits those. So take, for example, today we may have certain architectures that make it very easy to make things scale up, but they may inhibit our ability to reason about them, right? Because now we've just built a distributed system, okay? So that was the critical idea, is that beyond the functionality of your application, like I'm building an accounting app, the patterns that I use may make it easier to do certain things, like get low latency, but maybe make it hard to do other things, like make it more or less usable. And then finally, and this was so obvious, again, in hindsight, back in the 1990s, all of the architecture patterns we talked about were patterns in the runtime view. That is, like I run my code and it ends up being a client-server system where there's this chunk of running code over, say, in the browser, and here's a chunk of running code on the server. Okay, it's a runtime pattern. But really, there's patterns about how we organize the source code. And you might have a set of dependencies that are structured in a certain way. And you say, for example, no loops in my dependencies. Okay, well, that's a pattern in the runtime view. But we also had patterns in the deployment view. So we talk outside of Google, people talk about red-green deployments, okay? And that basically is the idea that some of our customers are seeing version 2 while some of our customers are seeing version 1. That's a deployment pattern. So that was the last sort of unlocking and generalization of patterns. Okay, the last chunk of architecture abstractions that I want to introduce deal with structure. So there are 3 of them here. Going back to 1975, we had rudimentary efforts to talk about module interconnection languages. Then we figured out that styles ensure qualities, not just are connected with them. And then finally, in the mid-90s, we figured out connectors. So the first one, module interconnection languages. This comes from what's considered to be a seminal paper in talking about software architecture. And here's a quick quote. Current languages discourage the accurate recording of the overall solution structure. They force us to write programs in which we are so preoccupied with the trees that we lose sight of the forest, as do the readers of our programs. This is a complaint that you could probably put into today's world as well. Like we write these little snippets of code and then trying to understand how those connect into our frameworks, how the frameworks orchestrate that code, and then how it gets into production and therefore it's going to behave is extraordinarily difficult. And in fact, that's what we spend a lot of our time doing, is trying to reassemble that structure, even though when we look at the source code, it's not really obvious from that. So the big idea here that was proposed in this paper was that there needs to be this other set of abstractions beyond just here are the modules, that is, here's the code. There needs to be a description of what's bigger than that. So it's more like a problem statement rather than a solution. In 1993, there was another abstraction that popped in here. So for example, not only do we, for example, have a client-server pattern, there's the idea that if we deliberately constrain ourselves and we either through discipline, don't stray from the architecture pattern, or maybe we've enforced it through architecture hoisting. That is, for example, in a MapReduce framework, you get called by the framework, like your mapper is going to run now, okay? So because of those styles, we may get certain qualities out. So for example, let's take MapReduce, because that one's critical for Google's history. The idea of MapReduce was it allowed Google to use commodity hardware, they're talking about early days, right, to make this search index that nobody thought we could build something so big, but we were able to take commodity systems and use the MapReduce architectural style such that we could scale up to internet size problems, okay? So that was really neat, that it wasn't convenient for programmers to have to write map jobs and reduce jobs, but it certainly was the enabling characteristic of how we wrote programs that allowed us to get to that kind of scale. So it's the styles ensure a particular kind of thing. In this case, it's scalability. The next critical abstraction here is that of connectors. Here's the old idea. Whenever people draw software diagrams, they draw boxes, and of course inside the boxes there's more boxes. So for example, if I said here's my server, well, inside my server there might be a box for parsing and another box for doing the business logic and another box for persistence. That's just a standard sort of pattern. What we hadn't figured out until the 1990s was the same kinds of things happen for connectors. And I'm not going to try to give a full explanation of this, but the short version is when you draw a line between any two boxes in your diagrams, a lot of times there's a set of nested boxes inside that connector, okay? And that in fact, when you do something that you consider to be synchronous, that for example, that when I make this call, I'm gonna block until the return value comes, it's usually built in terms of other smaller primitives that may be asynchronous. And so that's just one example of our connector's nest. And it allows a certain level of abstraction that lets me stand away from the fact that, well, really, I understand under the covers, TCP IP is going on here, and these are just little packets flying back and forth. But as far as my architecture's abstraction is concerned, this is a synchronous call. I call the server, and it gives me back a response, okay? So that was the overall set of architecture insights. I know it's a bunch to digest, but what I want you to take away from all of this is that back in the 90s, we were seeking out a set of abstractions that we wanted to say, these are the software architecture abstractions, and they allow me to think about my project. I can use these abstractions on pretty much any project, no matter what kind it is. That is, these are universal abstractions. And what's more, they're not quirky and for my particular project that it's inside my head. A different developer would have a different set of abstractions. No, these were meant to be a set of abstractions that all projects can use to some extent, although they may need to invent their own, and that these are abstractions that should span developers, okay? So they're not George's quirky abstractions, they're in fact the team's abstractions. So let me give you a quick summary. The idea of what is software architecture can be seen as three different answers that people have given over time. First is that it's a social construct. In other words, this is the least constrained. Whatever we decide is our design, okay? And you shouldn't expect that George's set of abstractions should be any different than anyone else's abstract. You shouldn't expect my abstractions to be similar to other people's, okay? It's just whatever I say they are. The second view of this is that software architecture is a bunch of decisions. And of course, we know we make decisions in projects. And if you group decisions into easy to change and hard to change, the architecture decisions are the hard to change abstractions, or sorry, hard to change decisions. And then the third view, the one that I'm most connected with, that I think works the best, is that actually software architecture is a specific set of abstractions that let us reason through software, and that these are reasonably universal abstractions. So going back to what I mean about universal abstractions, if I described three different ways of building a system, I could draw a diagram that would sort of give me insight into those. Those diagrams or those abstractions would allow me to do reasoning, and it would let me take concrete problems that I have and move them up into this abstraction such that I could operate on them, think through them clearly, and then I can go and build the next version of software. Of course, all this came about because a coworker asked this just fantastic question that I had taken for granted because I'm so deep inside my perspective. He said, I think about software architecture as the set of design decisions that are hard to change. And that's a perfectly reasonable and widely held perspective these days. So with this talk, which has gone on way longer than I'd hoped it would, the idea is there's all these different perspectives. The one that I subscribe to is the architecture is a set of abstractions. And that's underlying this article. Why is it getting harder to apply software architecture abstractions? Because we're in this frantic, iterative factory mindset of like write some code, push it into production, write some code, push it into production. And we have a hard time making room to think about those abstractions that span the system, right? That give us insight into how the system is going to behave. And instead, we lean on the kind of quick feedback loops, right? To say, well, I pushed it into production, I got these signals from production, and I'm going to use it that way. So that's what that article and the context is about, okay? Thanks, you guys, for listening, and I'll talk to you again soon.